Like Gideon, I'll be taking through Fermat's little theorem. So, Fermat's little theorem is a fundamental result that helps you to calculate powers modulo n when n is a prime number. So this is the function of finding the Fermat's little theorem, which is a p minus 1 congruence 1 modulo p. P is a prime number and a is a number that is not multiple of p. So take for example, let p be a prime number and let a be an integer that is not multiple of p. Then take for example the finding the modulo of 13. So our 6 is a, which is not the multiple of 13. So our power will be 13 minus 1, which is 12. This statement is correct. So this congruence may fail if n or p is not a prime. For example, if n is 4 and a is equal to 2, then 2 raised power 4 is congruent 16, congruent 0 is not congruent of 2 modulo 4. So let's take an example to apply Fermat's little theorem. Take an example of 4 raised power 20 modulo 7. So let's give our formula a p minus 1 congruence 1 modulo 7. So it will be 4 raised power 6, which is 7 minus 1, which is 6, congruence 1 mod 7. So let's guess the powers that will result to 4 raised power 20. So it will, let's test this one, 4, 12, congruent 4 raised power 6 power 2 congruent 1 squared congruent 1 mod 7. This one is far away, so we check for the next one, which is 4 raised power 18, which is 4 power 6 raised power 3 congruent 1 raised power 3 congruent 1 mod 7. So we take the powers. So our power was 20. So we take 20 equals to 6 times 3. 6 times 3, which is 18. This 18 plus 2, our remainder 2. So here is 6 times 3, it is 18 plus 2 is 20. So we take 1 power 3 times 4 raised power 2, which is equals to 2. Yeah, that's the answer.
I'm going to take you through a topic in check digits. So let's get started. So check digits, it's a methodology which is used in validating the barcode numbers. So in groceries, often have identification numbers, such as in businesses, so printed on them, accompanied by a barcode. So a barcode is just a way of formatting the identification number so that it can be easily be read by a scanner, then identified from a database on a computer. So errors while reading these numbers, errors might occur in communicating identification numbers. So for example, a shop assistant may type an identification number incorrectly into a cash register. So to help prevent such kind of an errors, so we use the last digit to check the validity of these digits. So for example, let's check a digit for the international standard book number using the modular arithmetic. So the international standard book number digits are for example, are the 0, 1, 4, 1, 3, 9, 1, 5, 2, 9. So let's label the digits A1, A2 to A10. These A1, A2, A3 are going to represent the digits, the number, the individual numbers of the digits. So in reverse order. So we are going to write them in reverse order, so that the A1 in the check digit as shown. So the A10, A9, A8, A7 to A1. So we are going to write them in the reverse order as I have shown you. So the check digit A1 is then defined to be the integer from 0 to 10. That satisfied this kind of an equation which says that A1 congruent to negative 2 times A2 minus 3 times A3 minus 4 times A4 minus 5 times A5 to 10 A10 modulo 11. So by rearranging this kind of an equation, we get this equation below here, which says that A1 plus 2A2 plus 3A3 all the way to 10 A10, which is congruent to 0 modulo 11. So an SBN must satisfy the congruence in order to be valid. So when the A1 is 10, when we have this A1 here, so when A1 is 10, this A1, we represent it by X, which is a single symbol. It is represented to ensure that we have a single symbol. So let's compute the above example, which I have shown you in the above here. So here, our A1 from the above example, our A1 is going to be 9. So it's going to be 1 times 9 plus 2 times 2 plus 3 times 5 plus 4 times 1 plus 5 times 9 plus 6 times 3 plus 7 times 1 plus 8 times 4 plus 9 times 1 plus 10 and 0. So from here we are going to get 9 plus 4 plus 15 plus 4 plus 45 plus 18 plus 7 plus 32 plus 9 plus 0. So the sum of the above, we are going to get 143. So 143, if it's divided by 11, it's going to give us an answer of 13. So which means that 143 is going to be 0 modulo 11. So if we get an answer to be 0, it means that the validity, it means that the barcode number, it is valid. So as we have found in the above example. So when we are getting this kind of validity, for us to get to validate these numbers, there are two types of errors which can occur. So the first error is by interchanging the numbers in between. So if we have a number like 1, 2, 3, 4, 5, 6, 7, 8, 9, and x. Remember, an x is a numeral. It's going to be a Roman numeral representing 10. We're going to represent that to signify a single number. So you can interchange either 5 and 6. You find that is one of the most common errors which is found. And another error is going to be, it's done when someone is interchanging or typing incorrect starting number. So that's all about the check digits for now.
My name is George Kipto, and I'm going to take you through multiplicative inverses. So multiplicative inverses are inverses modulo n that gives a way of dividing in modular arithmetic. So we use them to solve linear congruences such as 5x, which is modulo 2 mod 12, where x is unknown. Considering the congruence 20 mod 8, congruence 8 mod 6. So even though 20 and 8 are divisible by 4, like 20 divided by 4 is 5, and 8 divided by 4 is 2. You cannot divide both of the congruents by 4 because 5 is not congruent to 2 mod 6. So in modular arithmetic, only numbers used are integers, so we cannot multiply by the fraction. Instead, we need numbers that can perform the same role as reciprocals, called multiple inverses modulo n. For example, in the equation AV modulo 1 mod 6 mod n, a multiplicative inverse of modulo n is an integer v such that 1 is mod n. In an example, 5 is a multiplicative inverse of 2. 5 is a multiplicative inverse of 2 modulo n because 2 times 5 is congruent to 1 mod 9. For some integers a and let's say for an integer a and positive integer n, there is no multiplicative inverse of a modulo n. In an example, 3 does not have a multiplicative inverse modulo n, modulo 9. To see this, suppose that 3v congruent 1 mod 9. From this method explained, congruence is equivalent to the statement that 3v is equal to 1 plus 9k for some integer k. However, the left hand side of this equation is divisible by 3, but the right hand side is not divisible by 3 because 3 is a factor of 9k. Adding 1 makes it one more than the multiple of 3. This is impossible, and so 3 does not have a multiplicative inverse modulo 9 after all. Then I'm going to introduce the concept of coprime. Two integers whose highest common factor is said to be 1. So two integers whose highest common factor is 1 are said to be coprime. So all coprime numbers, their HCF is 1. Let's say if a and 9 are coprime integers, then a does not have a multiplicative inverse modulo mod 9. Multiplicative modulo 9. To see this, the Bezout identity tells us that if the highest common factor of a and 9 is 1, then the integers v and w are such that a v plus 9w is equal to 1. Therefore, av is equal to 1 minus 9w. Using the method of writing a congruence equation in the reverse, we say that av congruent 1 mod 9. Therefore, v is a multiplicative inverse of modular 9. Sometimes you'll be able to find a multiplicative inverse with an intelligent guess without using either of these methods. For example, when you want to find a multiplicative inverse of 29 modulo 30, you just need to observe that 29 congruent negative 1 mod 30. So multiplying 29 on the other side will be 29 times 29 congruent minus 1 times minus 1, which is congruent to 1 mod 30. Here you are able to see that 29 is in its own a multiplicative inverse of modulo 30.
Oh, my name is Uche Kame Collins, and I'm going to pass you through linear congruence.
Oh, so a linear congruence is a congruence in the form. So majorly a linear congruence is expressed in the form, let's say ax, which is congruent to b modulo n. So we have this b, a and b, they are known values. So these are known values, and the value and x is an unknown value. X is an unknown value. So the process of solving the process of finding the values of x, which is the linear congruence is true, is called solving. So we want process of finding this value of x is the process of we call solving process. Higher, solving the linear congruence, the linear congruence. Any number x for which the linear congruence is true is a solution. So it brings to us what's a solution. Solution is any number x for which the linear congruence is true. Any number x for which the linear congruence is true. The linear congruence is true. Higher, the solution of a given linear congruence is in the form. So now the solution of that linear congruence, of the linear congruence is in the form x is congruent to C mod n. So let's say this is an example, like 5x congruent 6 mod 9. So we want to find like the x value. So for any value, this is congruent to 1 mod 9. So now we want to find the value of x. So like this will be 5 times 2 is congruent to 10, which is equals to, is congruent to 1 mod 9. So now this x is equals to this, the value of VB mod 9. Now we want to find like x. So x is equals to these two that we have gotten here, this 2 times 6, which is congruent to 12. Now 2 times 6 is 12, and then which is congruent to 3. So x is equals to 3 mod 9.
Okay, I'll be taking you through Affine Ciphers. Affine Ciphers is used for deciphering and enciphering messages. So before any information is being transmitted, it has to be transformed in order for the intended recipient to get it. So the algorithm used for transforming this kind of messages is called a cipher, and the process of designing this kind of ciphers is called cryptography. So one particular type of a cipher which is being used is called an affine cipher, which uses some theory of linear congruences, as you have seen earlier. So before you carry around an affine cipher, you must first replace every letter of your message with a number. So that one can be facilitated by the use of this kind of a table below here. So let's take for an example, if you want to replace this kind of a message called hullabaloo. So this one, you have to replace it with its corresponding number. So like H, it is being like H, you have to replace it with 7. You have to replace it with the 20. L, you have to replace it with 11 and 11. A, you have to replace it with 0. B, you have to replace 1. A with 0. L with 11. O with 14 and 14 respectively. So then, after that, you have to apply the enciphering process to cipher the above message. So this can be applied by the rule that says that you should replace the integer x, in which here the integer, it's the individual digits replaced in the above. So you have to say that you have to replace the integer x with the integer e of x from 0 to 25, in which 0 to 25 represents the letters of the alphabetical letters. That satisfies, this is the rule. There's an example of a rule which says that e of x concurrent with 5x plus 23 modulo 26. So let's use this rule to cipher the above information. So let's say, like for example, we take 7. So e, like for example, e of So let's take for an example, if we want to encipher the digit 0. So we have to replace with x 0. So we will take 5 times 0 is going to be 0 plus 23 is going to be 23. If we divide 23 by 26, we have to get a remainder of 23. So that the same thing will happen to 1, which we have to replace it with, by on our x by 1. It's going to be 5 times 1 plus 23, which is going to be 28. Which 28, if we apply the modulo of 26 on 28, we're going to get a remainder of 2. So which means that our next cipher digit is going to be 2. So on our message 7, 20, 11, 11, 0, 1, 0, 11, 11, 14, and 14, it becomes, if we apply the above cipher rule, we are going to get 7, we replace 7 on 5, it's going to be 35. 35 plus 23 is going to be 58. So if we apply 58, we apply modulo 26 on 58, 26 goes to 58 2 times. 58 divided by 26 going to be 6 times, with the remainder, it's going to be 2 times the remainder of 6. So this 6 becomes our next cipher digit. So this process goes on until we get the whole message being enciphered. So the affine rule, which we were using above, works out the following. So the affine cipher, an affine cipher modulo 26, it's a rule for reordering the integers 0, 1, 2 up to 25. These ones, they represent the letters on our alphabetical alphabets, all the alphabetical whatever. So E of x concurrent ax plus b modulo 26, where a and b are integers and a and 26 are coprime, in which the coprime, they only share one factorial, which is 1. So that's all the process of ciphering the messages. So the process of recovering the original message from the enciphered message, it is the other way around, which is called the deciphering. So this has to be done if you have the affine cipher. You have to use the affine cipher to encipher the encrypted message. So the deciphering rule for affine cipher is given below. So the rule says that the rule D for deciphering the affine cipher E of x concurrent ax plus b modulo 26, which modulo 26 represents the number of alphabets we have, is given by the b of y concurrent v, which is into y minus b modulo 26, where v is a multiplicative inverse of a modulo 26. So that's all about deciphering the enciphered message.
You receive the following message that have been enciphered using the specified cipher E, which the message is 14, 10, 6, 22, 22. Using the encipher function 5x plus 10 mod 26. This is our table. We start A is 0 and then Z is 25. So we write our equation 5x congruence 5x. This is the encryption function 5x plus 10 mod 26. Because this 5 and 26 is a coprime number, which is their HCF is equal to 1, we apply the multiplicable inverses, which says that 5v congruence 1 mod 26. We need to find the value of v. So our value of v will be 5 times negative 5 congruence negative 25 congruence 1 mod 26. This value of v, by using our decipher function, which is dy congruence v y minus, we use this 10 minus 10 mod 26. We need to find the value of, we have the value of y, we have the value of v and the value of y. We need to find the residue. So it's d, our value of y will be the first one, which is 14 congruence v, our v is negative 5, our y is this 14 minus 10 mod 26. Here is equals to negative 20 mod 26. Negative 20 mod 26. The answer is 6. So our first letter will be 6. So let's apply to the next character, which is d. 10 congruent, our v is negative 5, v is negative 5, 10 minus 10 mod 26. So it's equal to 0 mod 26, which our answer is equals to 0. d6 congruent negative 5, 6 minus 10 mod 26. 4 times negative 5, that is negative 20 mod 26. So 26 goes into negative 20, 0 residue 20. Or it is positive, not positive 20. 26 goes here, 0, remainder 26, remainder 20. D22 it is congruent negative 5, 22 minus 10 mod 26. Negative 60 mod 26. 26 goes here, 2 times remain 18. So our characters with 6 is 6, 0, 20, 18. Then 22 will remain 18. So it is 18, 18. So when you come to check, 6 is G, 0 is A, 20 is U, 18 is S. So our name is Gauss. Second, suppose the word 22, 8, 11, 22, 9 has been enciphered using the affine cipher, which is EX congruence 9x, negative 9x plus 6 mod 26. So because 9 and 26 they are the co-prime they have the HCF of 1, we'll apply the multiplicative inverses. So we'll look for a number which is negative 9 v congruent 1 mod 26. So we look for the value of v to give us the residue of 1. So it is negative 9 times negative 3 congruent 27 congruent 1 mod 26. So you'll find the value of v, which is negative 3. So our deciphering function will be dy congruent v y minus 6 mod 26 mod 26. So our y is 22, d 22 congruent v, our v is negative 3, our y is 22 minus 6 mod 26. So 22 minus 6 times negative 3, that is negative 48 mod 26, which is equals to 4. We go to our next character, which is d8 congruent v. Our v is negative 3, our y is 8 minus 6 mod 26. Is equals to negative 6 mod 26. Our answer is 20. Our residue is 20. So d of 11 congruent, d of 11 congruent, our v is negative 3, 11 minus 6 mod 26. So negative 3, 11 minus 6 times negative 3, that is negative 15 mod 26, which is 11. Our 22 will remain 4, so we'll go to 9. d9 equals congruent negative 3, 9 minus 6 mod 26. Negative 9 minus 6 times 3, negative 3, that is negative 9 mod 26, which is equals to 17. So our character is equals to 4, 20, 11, 11, 4, 17. 4 is U, 20 is U, 11 is L, Our character is 4, 20, 11, 4, 17. So EU, 4 is E, 20 is U, 11 is L, then 4 is E, 17 is R. Our word is Euler.